Good morning. The last class we have introduced the Domino CMOS, and I just told you at the end that to work out an example. I do not know whether you tried or not, but I will do it today. Before I go to that, I will discuss another kind of Domino CMOS apart from the one which I discussed in the last class. The last class one, you remember I told that there are two blocks, for example. We said it is F1 block, this is the F2 block. These F1 and F2 blocks are realized by AND or AND logic. Then we have got the two transistors on either side. So this I discussed in the last class, what is the need for putting the inverter at this point to avoid the discharge of this particular node during some particular instance of cycle, the evaluate phase. And I discussed that if you directly cascade such stages, the so-called Precharged logic stages, there may be some problems. To get rid of that problem, we interpose, we just put in between the two stages one inverter, and that solves the problems. This was clearly discussed in the last class. Now there is another version of the Domino CMOS example, the Domino CMOS available. Here you remember, in the case of Domino CMOS, excepting for the PMOS loads, PMOS, these transistors, so-called the transistors through which precharging is done, apart from them, all other transistors are in MOSFETs, and therefore it is a very dense circuit, it is a very compact circuit. On the other hand, there is another kind of Domino CMOS, which is realized using both nMOS and PMOS as follows. Let us see. So here you see that the second example as compared to the first, you see that this here the F1 block is made of all nMOS transistors, nMOSFETs. Whereas the second block F2, here I call it F2 dashed, consists of P MOSFETs. That is why I call it P block. So this is N block and this is P block. And we do not apply the same clock, but alternatively you apply phi and phi inverse, phi and phi bar. Okay? And instead of putting any inverter in between, I directly cascade it. Can you tell me how it works? This particular one. Please remember now that this Domino CMOS example, Domino CMOS circuit topology, a circuit configuration, does no longer consist of mostly N MOSFETs. Rather, we are using in alternate stages N transistor N MOSFETs and P MOSFETs and combining them efficiently in order to avoid the inverter in between. But how it works? Also, I have to provide not only phi but also phi bar clock alternatively to the different stages. It's a very interesting one, but there are a lot of disadvantages. That is why this configuration is no longer popular, but it was a very good proposition in the beginning. You see here, you just carefully see that this block, all the transistors in this block as well as this one, they are PMOS. Now suppose the same case which we are considering in the last class, that suppose this during a particular evaluation cycle, the F1 bar, this point where we get F1 inverse, that should go to 0. In the prior Precharged phase, this node was at 1, that means VDD. But then I am thinking that as soon as I apply phi is equal to 1, so that this transistor gets off, whereas this becomes on, at this point I should now get 0, because that is what I am assuming. That combination of the logic is such, input variables is such, that it should be 0. But it does not happen. There is a small delay, and that becomes 0, 1 to 0 after a small time interval tau, which is the propagation delay of a particular edge, leading edge or trailing edge, whatever you call it. Okay? Then there is over a small duration of time, the 1 is extended even beyond the Precharged phase. But look at these transistors. When phi is 1, that is the evaluate phase, then phi bar is 0. You just see, when phi was 0, then phi bar was 1. So which transistor was on of these two? This one is on. Therefore, and you see that the output node is like this, then it will go to the next stage. It swings like this, and then like this, like this, like this, and so on. So there is some kind of some kind of domino from here to there, and then like this, like this, like this. It goes. Now what happens? This output node is now Precharged. You can call it pre-discharge instead of calling Precharge, but the proper word should be Precharged to VSS. When phi is 0, this node is Precharged to 1 or VDD, and this node is Precharged to 0 or 0 volt, or you can call it, in fact, it will be discharged. Actually, you see that whatever, if it is ground, then whatever charge was there, it will be dissipated to ground. It will all go to the ground, and therefore this node will be Precharged to 0 volt. Okay? Then when phi becomes high, this transistor gets off. And this one, as I told you, for the particular example, there was a transition from 1 to 0, that 1 was extended by tau. But then when it was 1, when it was all 1, then what was the state of the transistors here? The transistor gates, which are driven by this F1 dash, this output, they are off or on during that small tau period. You see that during that small tau period, when F1 continued to remain at 1, after during the just after the evaluation phase, what will be the state of the transistors to whose gates this F1 bar, the output are connected, output is connected? On or off? Off. So if this is off, then the state, there will be no problem. This whatever the state here, that will be maintained. There will be no question of suddenly this point goes to VDD. This point is not arising at all. It now depends on the combination of the input variables Y to decide the output at this point. Similarly, it will go to this next stage. Again, another F3 block is coming. The F3 will consist of N transistors. This will now be connected to, this will be now from this output to this A block. Similarly, and then thereafter from here, and it will go on. So please see that output has to be taken. If it is a P block Precharged logic, then output has to be taken from this point, not the upper point, but the lower point. Whereas if the transistors are all consisting of N transistors, all the A block transistors, F1 block transistors at N MOSFETs, then you have to connect the output from the upper node. So that's the thing. So in this case, one advantage is that you avoid using an inverter, and that saves space. Is it really very good? By doing so, the inverter is being avoided, and that glitch problem and other problem which was discussed in the last class, that will no longer be there. But is it a very convenient one? No, I don't think so. It is very good, because you have to use again another isolation, NOL, to incorporate PMOS space and so on and so forth. It consumes a lot of space. Just by putting two NMOS FETs as an inverter, it is found practically that putting another NOL perhaps usually occupies more area than before. And we shall see afterward, and not see, I think we have discussed before also. It is the PMOS in NOL which are more difficult to design and fabricate rather than the NMOSs on the substrate. So if we can try to avoid PMOS space as far as possible, it is convenient not only from the realization point of view but also from the design point of view. So that is, therefore, this one, it was a very good proposition theoretically, but it really did not stay, it did not continue, and it is this kind of configuration which is still very popular. Now, as I told you, I will now treat one very practical example of realizing an nMOS, a Domino CMOS logic. Let us consider, suppose I want to realize a function f is equal to, which I told you to do. I do not know whether you have done it or not. As I told you, this could be realized by a single block without cascading. But to demonstrate the advantages of Domino CMOS, I will try to realize it with using a three cascaded stages. Let me just explain. Now we can write this f as some x1, x2 plus x3, where x1 is AB plus CD, x2 is A plus B plus C, and x3 is A, B, C. This is basically, you see, then AND OR operation. This is a typical OR operation, and this is an AND operation. And by combining them, I am getting the function f. That's the thing. We can write it like this. Now, suppose I want to realize it, as I told you, let us assume that we can realize it using a three-stage Domino CMOS logic. So I will just draw it like this in this case. So what I assume that it is possible to realize f, the function f, using 3 domino CMOS stages coupled via inverters as indicated here. And there are 3 functional blocks involved, F1, F2 and F3. Let's see whether, initially I assume that there is no such inverter. Let us forget about the inverters. We shall discuss that without inverter, we shall discuss first without inverter and then with inverter. There is no inverter in the beginning, no inverter. No inverter. You see that ultimately the functional block F3 at the output you will get F3 bar. Okay, so you now can just write like this. You see that our F3 therefore is equal to F bar, and what is F bar is X1. You just check yourself, X1 X2 plus X3 complement, and that can be written as X1 X2 bar dot X3 bar, and that is equal to X1 X2 bar, whereas X3 bar is your X3 is A, B, C, so X3 bar is simply A bar plus B bar plus C bar, and I call it F2 bar A bar plus B bar plus C bar. Please note X3 is equal to ABC, therefore X3 bar is this one, and you can write where naturally F2 is equal to X1 X2. I have assumed that F2 is equal to X1 X2, so that this is as if the function F3 has been realized from the variables A, B, C. That means it is the OR gate of A bar, B bar and C bar and F2 bar. F2 bar is coming from the earlier stage. F2 bar is coming from the earlier stage, from this stage. So I have said that this is all F1 bar now because there is no inverter. F1 bar, F1 bar, F2 bar, F2 bar. So this F3 function is a function of A bar, B bar, C bar or and F2 bar, which is derived from the last stage, whereas F2 is equal to X1 S2. Now F2, as I said, that is therefore equal to X1 X2, and what is X, and that is equal to X1, and what is X2? X2 is A plus B plus C. A plus B plus C, and that we write it as F1 bar into A plus B plus C. In the same way, I can say that F2 function is produced for F2, this block F2 is F1 bar, A, B, C or and F1 bar. F1 bar is derived from the last stage. Okay, F1 bar is derived from the last stage. So same way I can write, and as it is, you just see that in F1 is therefore F1 bar is X1, so F1 is equal to simply X1 bar, and that is what is X1? ABC plus CD. So it is equal to AB plus CD inverse, and that is equal to AB inverse CD inverse, and that is ultimately equal to A plus B and C plus D. Is it all right? Let me repeat. The function f is actually F3 bar. According to this thing, I am assuming this is a function to be realized. So f is nothing but equal to F3 bar. Therefore, F3 is equal to F bar. and that can be written like this. It is the AND function of F2 bar and or of A bar, B bar, C bar. So A bar, B bar, C bar are nothing but the variables being inputted to the function F3 here, whereas F2 bar is derived from the second stage. So this is this one. From here you see that F2 is equal to X1, F2 is simply equal to X1, X2. Therefore, it can be rewritten as finally F1 bar A plus B plus C. In the same way, you can therefore say the functional block F2 can be realized from variables A, B, C, ORing them and ANDing them with F1 bar obtained from the first stage. And again, F1 is nothing, because F1 bar is nothing but X1, therefore F1 is X1 bar, which can be finally expressed like this. Therefore, F1, the function has to be simple. There is no input for, because this is just first block. It does not require any, it does not receive any input from an earlier stage. So simply equal to can be obtained by first ORing A bar, B bar, C bar, D bar, and then ANDing them. And ultimately, therefore, the structure becomes like this. F1 is to be produced by first ORing This is nothing but your F1 block. This is the F1 block. Then how do you get the F2 block? Simply so this is nothing but your F2 block. And ultimately F3 is same thing. And the functions are A bar, B bar, C bar. So that is your So ultimately you see that I have realized the same function F3 bar. F3 bar is nothing but our F, please remember this. by cascading 3 domino CMOS, Precharged CMOS logics. These are called individually Precharged CMOS logics. This is F1 block, at the output of which you are getting F1 bar, and that drives this transistor in F2 block because it is an AND function. It is nothing but F2 is equal to F1 bar into AND ABC, A plus B plus C. Similarly, this one produces F2 bar at the output. That drives the third block, and at the this is again OR of A bar, B bar, C bar, and F3 bar, and F2 bar, and to get F3 bar. So this is the standard one. Suppose you don't have that domino CMOS concept. We introduce the domino CMOS concept for certain reason, but suppose we have not suppose I do not know at all what domino CMOS is and blindly cascade 3 precharged logic stages derived in the way which I just now discussed. Then I think it is an example by which you can show, you can really understand what is the problem in this cascading, which I discussed earlier class, but now you can easily understand what is the problem in this cascading. Let us consider that. That is why I told you to just go through. Let us first assume that, first example, suppose A is 0, B is 1, the combination is such, B is 1, C is 1, and D is 1. This is the combination of the variables during a particular evaluation cycle. A0, B1, C1, D1. And in that case, during the evaluate phase, what will happen? During the evaluate phase, that means phi is 1. What will be the values of, what is the expected values of F1 bar, F2 bar, and F3 bar, and that is equal to F. And that should be, you can easily see that this will be 1, this will be 0, and the output will be 1. You can easily check by seeing that when A0, B1, C1, and B1, for A0 means this is on, and C1, D1, C1, D1. So the overall, this F1 block will represent an open circuit, and therefore I expect at this point 1. In this particular case, when A0, B1, C1, D1, what is happening? This is 1, means this transistor is on, and C1, D1 on, so this is a short circuit path. So this will be discharged to 0. So I expect F2 bar to be 0. Okay? And then F2 bar is 0 means this is open circuit, independent of whatever may be the state of the 3 transistors. This will again be 1, and F3 bar is 0. So that is the thing which you expect. But do you get this? Do you get this? You please check. Huh? The F2 bar is 0, so this transistor is off. F2 bar is, now F2 bar, sorry, F2 bar is 0 means this transistor is off. Transistor off means the whole thing is off, so it will, the feature state will continue, if there should be 1. There should be 1, it's okay. Now let us now see what happens. This is a clock phi, and I call this is pre-charge, this is evaluation, this is pre-charge, this is evaluation, and this is pre-charge that I have told you. Then what will be the state of F1 bar? During the pre-charge state, it is 1, and in the evaluation phase is also 1, therefore 1 will continue. And this will continue to remain 1 all through. This is a 0 line. Remains 1. What is F2 bar? During the evaluation phase, this is 1. During the precharge phase, it is 1. And then it should be 0. But naturally, this will happen after some time. So there will be a short delay involved. It will become 0 then. Then I get this point. Yeah. And of course, precharging takes place more quickly. So it will be like this. You see that our desired thing was 0, but that has happened during the evaluation phase, excepting for the small time initially, at the start of the evaluation phase, during which it is 1, but otherwise it is 0. Then what about F3? F3 bar. Now check what is going to happen for F3 bar. You just see what is going to happen now for F3 bar. You see that F2 bar is 1 for a short time. F2 bar is 1 for a short time. And what was the status of ABCD? I assume A0, B1, C1 and D1. B1, A0 means this transistor is on. A0 means A bar is 1, that this transistor is on. And F bar is on for a short time. F2 bar is on for a short time. So it provides a short circuit path during the short time tau. And the resistance may be so small that even during the short time, the whole charge, whatever accumulated here in the earlier pre-charge phase, may go. May or may not go. It may partially go or may fully go. It depends on you. And therefore, it will fall. Therefore, what is going to happen? It will just fall. And again, at the pre-charge cycle, it will rise. Then again, at the onset of this thing, it will fall. It cannot be 1. That's the drawback. Because if somehow the charge is lost from this, there is nobody to replenish the charge, because this transistor here, I have not shown the, please remember, I have not shown the transistors here, P MOSFETs or N MOSFETs here, I have just shown the blocks only. This transistor will remain off. If somehow the charge goes, there is no mechanism till the next pre-charge phase comes, there is no mechanism here to fill up that charge, to replenish the charge, therefore it will go to 0. This may not be 0, it may be a partial 0. Suppose that actually say our VOL is suppose 0.1 volt and VOH suppose is 4 volt. In that case, this one may not be 0.1 volt, maybe 0.5 volt, 1 volt, depending on how quick this process is. If it is a very quick process, it will not discharge fully. But one is discharged, this charge cannot come back here at this point, because this transistor remains off. That is a very important thing to be remembered. And so this is totally, here I am finding that F3 bar is practically is 0, which is undesirable. Actually what I need is, in actual case what I need is a thing like this for F3 bar. F3 bar should be equal to 1, and that is what is desirable. That is what is desirable. Similarly, you can check that the same thing is will go to happen for another. You can there are many other combinations. For example, if when A is 1, B is 0, C is 0, and D is also 0, you will find the same thing is repeating. It will not work properly. For the first case, you can easily say this has happened between the second and third, isn't it? You see that in this case, it is the F3 which has been affected, the output which has been affected. In the other case, it is F2 which will be affected. In the other case, when A is 1, B is 0, and C is 0, and D, F2 bar will be affected. You can check it yourself. Now, therefore, you will find that therefore this direct cascading, our conclusion is therefore that this such direct cascading is not permissible. You should not cascade them directly like this. Then you now try yourself how to make a domino version of that. This was without any domino, no inverter intermediate. Now try the version with domino. Okay, now redesign the logic blocks F1, F2, F3. Now you can call them F1 dash, F2 dash, F3 dash, such that in the presence of those inverters between stages, such that the function capital F is realized. You try yourself. Do it yourself. I'll perhaps discuss in the next class, but before I do that, go to the next class, I'll just give you some more examples. Try some other functions. Realize the following. So this is number 1. This is a number 2 problem. Following function. One is full adder, simple full adder. Two is, let us say, make a more very complicated one. Anyway,